NASA has calculated the exact probability that 4 astronauts will die on humanity's return to the moon, but they refuse to tell us what it is. While NASA calculated and publicly cited about a 1 in 276 chance of crew loss for SpaceX's first astronaut mission, NASA's Artemis II team explicitly refuses to release their internal survival numbers. The agency that once promised 1 in 100,000 safety odds for the shuttle, which actually killed crews at 1 in 68 rates, now says putting numbers on Artemis II would be misleading. Picture this: 4 astronauts strapped into a capsule atop the most powerful rocket NASA has ever flown, preparing to venture farther from Earth than any human in over half a century. Their destination isn't the familiar realm of low Earth orbit, where the International Space Station circles safely just 250 miles above our heads. They're heading into the cosmic deep, roughly 250,000 miles to the moon and back, carrying a heat shield that cracked and shed chunks of material on its only previous flight. Artemis II will be the first human journey beyond Earth orbit in over 50 years, sending 4 astronauts on a roughly 10-day trip around the moon, currently targeted for no earlier than April 2026. But this isn't Apollo, it's the second-ever flight of the most powerful rocket NASA has ever built, carrying a heat shield that suffered extensive and unexpected damage on its only test flight. NASA's own Inspector General estimates roughly 1 in 30 odds of mission failure for future Artemis lunar landings, with no rescue capability if things go wrong. The agency's silence on Artemis II's specific risks reveals a deeper truth about spaceflight: the gap between public expectations of safety and the reality of pushing into the unknown. This isn't just another space mission, it's humanity's first step back toward becoming a multi-planetary species. Yet NASA, the agency that has historically quantified every conceivable risk from micrometeorite impacts to toilet failures, suddenly goes silent when asked about the odds of their crew coming home alive. We'll examine the hidden risk assessment, the heat shield crisis NASA is flying through, and why the agency that put odds on everything else won't put odds on this. NASA has completed a full probabilistic risk assessment for Artemis II, but senior officials explicitly refuse to share the crew loss probability with the public. Think about that for a moment. Somewhere in NASA's files sits a document with a precise calculation of how likely these 4 astronauts are to die, and they've decided we can't handle that information. John Honeycutt, Artemis II Mission Management Chair, offered only cryptic hints during a NASA media briefing. He said first flights historically have about 1 in 2 odds of major failure. For Artemis II, he suggested somewhere between 1 in 2 and 1 in 50, while emphasizing NASA won't lay probabilistic numbers on the table. That's a range so broad it's essentially meaningless, like saying a flight will take somewhere between 2 hours and 2 days. This contrasts sharply with commercial crew programs, where NASA published detailed risk assessments with surgical precision. NASA calculated and publicly cited SpaceX Demo 2's risk as about 1 in 276 crew loss, and Boeing Starliners as roughly 1 in 295. These numbers came with extensive documentation, failure mode analyses, and public justification for every decimal point. The NASA Inspector General revealed that future Artemis lunar missions carry about 1 in 30 overall failure risk and 1 in 40 risk during lunar operations, with 0 rescue capability. Compare that to commercial crews' 1 in 270 odds, and you're looking at missions nearly 10 times more dangerous. But those are future missions with lunar landings. Artemis II is just a flyby, so why the silence? Historical context shows NASA's risk estimates are often catastrophically wrong, and not in the conservative direction. Shuttle managers believed 1 in 100,000 crew loss odds, while later analysis showed early flights were actually 1 in 9 to 1 in 12. That's not a small miscalculation, that's being off by a factor of over 1,000. Apollo crews faced about 1 in 10 odds of death per lunar mission according to retrospective analysis, though NASA never published those numbers at the time. The agency's current reluctance stems from multiple factors: sparse data from only one SLS flight, a painful history of miscalibrated confidence, and the political reality that admitting high danger levels could kill the program before it starts. Lori Glaze, NASA's acting exploration chief, said she's being really careful not to put a number on it because risk models work better for comparing design options than making public promises. But there's a more fundamental difference driving NASA's silence. commercial crew operates in the relative safety of low Earth orbit, just hours away from the International Space Station with multiple rescue options. Artemis II ventures into a realm where rescue isn't just difficult, it's impossible. When you're that far from home, when Earth appears as just a pale blue dot in the cosmic black, the math changes completely. The margin for error shrinks to zero, and every system failure becomes potentially fatal. Artemis I's Orion capsule returned from the Moon in December 2022 with what NASA delicately called unexpected thermal performance, a euphemism for a heat shield that looked like it had been attacked with a sledgehammer. Over 100 locations showed where chunks of protective material cracked and flaked off during the 25,000-mile-per-hour re-entry. Imagine chunks of your spacecraft's most critical safety system simply falling off as you plunge through Earth's atmosphere at speeds that would vaporize any unprotected object. NASA's Inspector General called the heat shield anomaly one of the most significant threats to crew safety that must be resolved before flight. That's Inspector General speak, for this could kill everyone aboard. After 2 years of investigation involving hundreds of engineers and millions of dollars in analysis, NASA discovered the root cause. During Artemis I's skip re-entry, gases became trapped inside the heat shield material faster than they could vent, causing explosive pressure buildup and cracking. Picture a pressure cooker with a blocked valve. The trapped gas has to go somewhere, and when it can't escape gradually, it explodes outward, taking chunks of heat shield material with it. This wasn't a minor design flaw, it was a fundamental misunderstanding of how the heat shield would behave under real flight conditions. Rather than replace the Artemis II heat shield, which would cost hundreds of millions of dollars and delay the mission by years, NASA chose to modify the re-entry trajectory to avoid the conditions that caused the damage. It's like discovering your car's brakes fail at highway speeds and deciding to just drive slower rather than fix the brakes. The fix has never been tested in full-scale flight. It relies on computer modeling and small-scale arc-jet testing, not another uncrewed demonstration. Former NASA astronaut Charlie Camarda, who survived the Columbia disaster and dedicated his career to spacecraft safety, calls flying crew without replacing the heat shield or conducting another test, playing Russian roulette. He sees uncomfortable echoes of Challenger and Columbia in NASA's decision to proceed based on analysis rather than proven hardware. These aren't the words of a risk-averse outsider. This is a man who has lived through NASA's darkest moments, speaking from hard-earned experience. NASA managers unanimously agreed they could develop acceptable flight rationale to proceed with operational changes rather than hardware replacement. The modified re-entry will use a shallower heating profile, spreading the thermal load over more time and distance, and target splashdown closer to San Diego instead of off Baja California. It's an elegant solution on paper, but paper doesn't have to survive 5,000-degree plasma at hypersonic speeds. Artemis I's cabin stayed in the mid-70s Fahrenheit despite the heat shield damage, proving the crew would have survived that particular re-entry. But the char loss reduced safety margins in ways not predicted by pre-flight models, and margins are what keep astronauts alive when everything else goes wrong. Critics argue this represents normalization of deviance, the same psychological trap that led to Challenger and Columbia, accepting anomalous behavior based on limited analysis rather than proven solutions. The deeper concern isn't just the heat shield damage itself, but what it reveals about NASA's understanding of their own spacecraft. If they got something this fundamental wrong on the first flight, what other surprises await in the unforgiving environment of deep space? Artemis II will take humans through the Van Allen radiation belts and beyond Earth's protective magnetosphere for the first time since 1972. Earth's magnetic field acts like an invisible shield, deflecting most of the universe's radiation away from our planet. Step outside that protection, and you enter a realm where the cosmos itself becomes hostile to human life. The crew will face 3 distinct radiation sources during their 10-day journey. Trapped particles in the Van Allen belts that surround Earth like invisible donuts of deadly energy, solar particle events triggered by massive explosions on the sun's surface, and galactic cosmic rays, the remnants of ancient supernovas that have been racing through space for millions of years. Expected total radiation dose is roughly equivalent to a whole-body CT scan, modest but non-trivial exposure that represents more radiation than most people receive in an entire year. The greatest acute threat comes from solar particle events triggered by solar flares, which can raise radiation levels to potentially lethal amounts within hours. These aren't gradual increases you can plan for. They're radiation tsunamis that can flood the solar system with high-energy particles faster than any spacecraft can escape. Artemis II launches near solar maximum, when our star reaches peak activity and flare probability is highest. Orion carries 6 radiation sensors distributed throughout the spacecraft that will trigger visual and audible alarms if radiation thresholds are exceeded, plus a designated storm shelter area beneath the cabin floor where crew can huddle during the worst exposure. Picture 4 astronauts crammed into a space the size of a large closet, surrounded by food and water supplies, waiting for an invisible cosmic storm to pass. NASA will monitor the sun continuously using ground-based observatories and space-based sensors, and even Mars's Perseverance rover, which can see dangerous sunspots rotating into Earth view days in advance. It's an early warning system spanning the solar system, but early warning doesn't eliminate the danger, it just gives you time to prepare for what you can't avoid. In testing, engineers found that repositioning stowed food, water, and supplies around the shelter significantly reduced simulated radiation exposure. Every bag of dried fruit, every water container becomes part of the spacecraft's radiation shielding. One of Artemis II's explicit test objectives is practicing building this ad hoc radiation shelter under realistic conditions, turning the crew into their own radiation protection engineers. The 24 Apollo astronauts who flew beyond Earth's magnetosphere show no clear excess of fatal cancers decades later, suggesting short lunar missions are tolerable from a lifetime risk perspective. But key Apollo missions flew during relatively quiet periods in the solar cycle, and their missions lasted days, not the weeks or months that future lunar bases will require. Artemis II represents far more than 4 lives hanging in the balance. It's the gateway to a $93 billion campaign to establish permanent human presence on the Moon and eventually Mars. Success unlocks Artemis III, originally planned as the first lunar South Pole landing, but now facing delays and possible restructuring as NASA focuses on testing Orion's integration with commercial human landers. The stakes couldn't be higher. Humanity's expansion into the solar system hangs on whether these 4 astronauts come home alive. The lunar South Pole holds water ice in permanently shadowed craters that have remained frozen for billions of years, a resource that could support life support systems and fuel production for Mars missions. It's not just scientific curiosity driving this program. It's the practical foundation for everything that comes after. Water means oxygen to breathe, hydrogen for rocket fuel, and the difference between sustainable exploration and impossibly expensive supply runs from Earth. The timeline reveals just how fragile our space ambitions really are. It took over 50 years to return humans to lunar vicinity after Apollo 17 in 1972 due to budget cuts, program cancellations, and the sheer technical complexity of deep space exploration. That's longer than the gap between the Wright brothers' first flight and the moon landing itself. The Constellation program, started in 2004 with great fanfare to return to the moon by 2020, was cancelled in 2010 as unsustainable, costing years of progress and billions in sunk costs. SLS development alone has suffered 6 years of delays and roughly $6 billion in cost increases, with per-launch costs around $4 billion, making each flight more expensive than some countries' entire space programs. An Artemis II failure would not only endanger 4 astronauts but could set back human lunar exploration by another generation. Unlike commercial crew missions that can abort to the International Space Station within hours, Artemis II has no rescue capability once committed to lunar trajectory. The crew will reach a maximum distance of roughly 250,000 miles from Earth, slightly exceeding Apollo 13's approximately 248,000-mile record, in a realm where rescue missions are impossible and self-rescue is the only option. This explains NASA's communications dilemma perfectly. How do you balance transparency about genuine danger with maintaining public and political support for humanity's next giant leap? How do you admit that space exploration remains inherently dangerous without killing the program that makes it possible? The political calculus is brutal. Congress has already expressed skepticism about Artemis costs and timelines. Admitting that Artemis II carries significant crew loss probability, perhaps approaching the 1 in 10 odds that Apollo crews faced, could provide ammunition for critics who want to cancel the program entirely. Yet hiding those risks feels like a betrayal of the transparency that democratic space programs should embody. NASA's refusal to publish Artemis II survival odds reveals the fundamental tension between public expectations of space safety and the reality of exploration. The agency learned from shuttle's false precision, promising 1 in 100,000 safety while delivering 1 in 68 mortality, that specific numbers can mislead more than inform. Precise probabilities create an illusion of certainty that simply doesn't exist when pushing into the unknown. But their silence also reflects uncomfortable truths that extend far beyond risk assessment. Artemis II is likely far riskier than the mature ISS taxi missions the public has grown accustomed to watching. We've become spoiled by the routine success of commercial crew flights, forgetting that those missions operate in the relatively safe harbor of low Earth orbit with multiple rescue options and decades of operational experience. With heat shield damage that's never been flight tested under the proposed fix, radiation exposure beyond Earth's protective magnetosphere, and no rescue options 248,000 miles from home, Artemis II carries risks reminiscent of the early Apollo missions, the ones where astronauts wrote their wills before launch and families gathered to pray for their safe return. The 4 Artemis II astronauts, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, will become the first humans to leave Earth orbit in over half a century, knowing the odds exist but not their precise measure. These aren't test pilots pushing experimental aircraft over desert ranges where failure means a parachute ride and an awkward conversation with investigators. They're explorers venturing into a realm where failure means death, where the nearest help is 250,000 miles away, where the margin for error approaches zero. They know this, accept this, even embrace this, because someone has to take the first step back toward the stars. Whether NASA's calculated silence protects the program or the public may depend on what those hidden numbers actually say. If the real odds are 1 in 50, the silence might be justified caution. If they're 1 in 10, the silence becomes a form of deception that undermines the democratic principles space exploration should embody. In April 2026, we'll learn whether NASA's confidence in their unspoken odds was justified or whether the agency's refusal to tell us the odds masked a gamble too stark for public consumption. The return to the moon was always going to be dangerous. The question is whether we can handle the truth about just how dangerous it really is, and whether our space program can survive that truth being told.